Okay, so we are being recorded, and so I'd like to thank you for joining the MAT 115 webinar on Euler diagrams. And I know it looks like Euler, but it's really pronounced Euler, like the oil you put in your car. So the Euler diagrams. And if you have any questions as we go throughout the webinar, you can use the chat box to type, and I will be checking that periodically. You can also use the Q&A box to type some questions. So I'll be checking as we go through the webinar, those two areas, and for what it is, you know, if you have any questions as we go throughout today's webinar. So to get started here, we're going to be looking at three main things with Euler diagrams. First, we're going to understand the difference between Venn diagrams and Euler diagrams because they look a lot alike, but they have some differences between them, and sometimes students get the two confused. So I want to set that straight, and we're going to draw some Euler diagrams with two sets, which means two circles. And we're also going to determine if an argument is valid or invalid using these Euler diagrams, which basically is why we're studying the Euler diagrams in the first place, is because we use it as a tool to determine if an argument is valid or invalid. So let's start by looking at the difference between Venn and Euler diagrams. Both of them are really useful for illustrating the relationships between sets. And the difference is, though, that Venn diagrams provide a region or like a space in the diagram for every possible situation between the sets, while the Euler diagrams only include the regions that are possible in the real world. So in the Venn diagrams, no matter the situation, if you have two circles or if you have three circles, they're always positioned the same way. But for Euler diagrams, they are positioned in such a way that matches the situation that we're looking at. So there's only the regions in the picture that go along with that particular situation. So the Euler diagrams can change from situation to situation. So let's look at an example. A Venn diagram, let's say we have two sets, and one is plants and one is birds. Okay, so a Venn diagram would include the intersection of plants and birds, which would be empty because there's nothing out there that's both a plant and a bird. So, but it would include a region for the intersection, while the Euler diagram would not include that region because there's nothing in the intersection between plants and birds. So the diagrams, just to give you an example what they would look like, the Venn diagram would have the both section, the region where plants and birds intersect, where they're both, it would be included in the picture. But for the Euler diagram, that region with both plants and birds is not included because there's nothing that would go there. It would be empty. So the Venn diagram includes that region because even though it's empty, it's still there. The Euler diagram leaves that off. Oh, and I just wanted to mention before we go any further that you don't have to frantically copy all of this down because when I'm done, I'm going to email, I'll post this in my classroom for students who have me, but if you have other instructors, I'm also going to send this file to all the MAT 115 instructors along with the recording. So go ahead and like frantically copy everything, okay? All right, so since the empty regions of the Venn diagram are left off the Euler diagram tends to be less complex because anything that's empty is left off. Okay, so that's the main difference between them. But let's look at some additional characteristics of Euler diagrams. One set completely inside the other set means it's a subset. So if you have the bears are a subset of animals that have fur. So the bear's circle is completely inside the animals that have fur circle, and so the bears is considered a subset of the animals that have hair set. Okay. And so that's another thing that we see with Euler diagrams is that sometimes if it's a subset, then the circle would be inside the other circle. Another thing we see with Euler diagrams is that we use an X to represent a single element in a set. For example, if this circle represents all of the pets with fur, then the X there is representing my dog Harley, where I'm picking out just one. That X is representing just one element of that whole set, pets with fur. So Euler diagrams, we use an X as well to single out elements whenever that makes sense to do in the situation. Okay, so let's take a look at different ways that we can draw these Euler diagrams with two sets. Let's say we have two sets A and B. So in this example, set A is a subset of set B, which is what I was just showing you a couple of slides ago. Let's see back here, where bears is a subset of animals that have hair. So sometimes you'll see diagrams like this, and it might be worded as like all A are B, like all bears are animals with hair. So in that case, the entire circle A would be inside the circle B. Okay. And I'm going to, let's see, someone says they can't hear me. Someone says they can hear me. If you need to hear me, I guess if you can't hear me, then me saying that won't do any good. But you need to call in if you can't hear. Okay. So let's take a look at another way we can draw. For example, here's an example of the all A or B. All cars have wheels. So the cars would be the subset, and the things with wheels would be the bigger set there. So that's an example. Okay, in this example, sets A and B have an empty intersection. So the intersection is not drawn, just like I showed you before with the plants and the birds. So this would be no A or B, where they do not overlap at all. There's no overlap. An example would be no car accidents happen on purpose. So car accidents would be in one set, things that happen on purpose would be in the other set, and there's no overlap. Okay, in this example, sets A and B have at least one element in their intersection. So whenever you have at least one there, we use the X to indicate that, saying that there it is, right there. The intersection is not empty. There is something in the overlap between sets A and B, and that's the idea of some A or B. So it's just saying that, you know, whatever is in set A is also in set B, that there's at least one thing there. Okay. For example, some cars are red. So you have red vehicles and you have cars, and there's an X there indicating that there's at least one car that is red when you say some cars are red. Okay. So another example, sets A and B may or may not have an element in the intersection, but in this example, let me go to the example and we'll come back to that. Some A are not B. So some A are not B is basically saying that there is at least one element in A that is not in B. So we draw it like this, and let me go back here. There may or may not have an element in the intersection. We're not sure about that, but there's definitely an element in A that is not B. So there could be something in the overlap between A and B, but we're not sure. We just know for sure that there is something in A that is not B. So some A or not B are is drawn like that. So I hope that, oh, and here's an example. Some calculators are not solar powered. So you have solar powered items, you have calculators. There may or may not be some solar powered calculators out there, but all the sentence is saying is that there's at least one calculator that is not solar powered. And just a reminder, if you have any questions, you can type in the Q&A box or in the chat box, and I'll be checking that periodically. Okay. Now, in deductive reasoning, we draw conclusions based on what's called premise statements, where we look at sentences, things that we assume to be true, and then based on those statements, we draw a conclusion. And the conclusion is valid when those premise statements support the conclusion. It should be support the conclusion. So what we're going to be doing is using Euler diagrams to determine if an argument is valid or invalid. Okay, so we used the 4 basic ones we just drew. We'll be using those, that idea to draw these pictures to determine if an argument is valid or invalid. Here's how it works. Now, before I get into the steps, I just want to mention that the reason we need a tool in the first place, the reason we need something like Euler diagrams in the first place to do this is because the words tend to get in the way of looking at the structure of the argument. We're really trying to see, does the conclusion, is it supported by the premise statements, meaning are there holes in the logic, or is it a sound logical argument? And so sometimes the subject matter of the argument can get in the way of looking at the structure of the argument. So we need a tool to be able to analyze how the argument's written. Does it make logical sense? Is there a flaw in the reasoning? Are there holes in the reasoning? Or is it a good, sound, logical argument? So we use the Euler diagram. It's one way that we have to just focus on that structure of the argument and to try not to let the content of what's being said get in the way, where if, for instance, the content is talking about the weather, we might be thinking about the weather instead of thinking about, is this a logical argument? So anyway, that's why we need a tool in the first place. So Euler diagrams is a really good tool to use for this. So it's basically 3 basic steps. Here's the first 2. We draw an Euler diagram based on the first premise statement. We're going to be looking at 2 premise statements. There can be more, but we're going to look at 2. So based on the first premise statement, we draw an Euler diagram. And then we use that same diagram to draw the second premise statement. So we're drawing one Euler diagram looking at the 2 premise statements, and we make sure that whenever we're drawing it, we include all the possible ways it could be drawn. Make sure we've gotten all the circles and the X's everywhere that they could be drawn. Okay, and while we're doing this, while we're doing steps 1 and 2, which is just looking at premise statement 1 and 2, we are completely ignoring the conclusion at this point. All we're doing is drawing a picture based on the premise statements. And then after that picture is drawn, it's like it's all drawn, you put your pencil down, now you ignore the premise statements, and then the third step, you just look at the conclusion. And if the conclusion if it contradicts anything in the picture, it's invalid. If it doesn't contradict anything in the picture, then it's valid. So you're just comparing then the conclusion with the picture, and you're ignoring the premise statements now. You're not paying attention to that. You're just looking at the picture. Okay. Now I want to mention that it's possible to have a valid premise, a valid argument that does not have a true conclusion. Valid and true are not the same thing. A conclusion can be true, but it could also be an invalid argument because we're looking at the structure of the argument, not the content of what's being stated. The conclusion might be very true, but if it's not based on the premise statements, it's an invalid argument. So because the argument's not just looking at, is the conclusion true? The argument is looking at all of the sentences put together and how they work together. So we're looking for, is there a flaw in the reasoning? And I see there's a question. Oh, it says, never mind. They can hear me now. Just periodically checking for questions. So we're just looking to see, is there a flaw in the reasoning? Not necessarily. We're not looking at, is the conclusion true or false? And we'll see some examples of this. It'll be easy to tell. So we use the Euler diagrams to study the logical flow of the argument, to see if there are any flaws or if the reasoning is sound. And the words of this tend to get in the way. The content of it tends to get in the way. So the diagrams help us just focus on the structure of the argument to see if it's a logical argument. Okay, so here's an example. Now, the horizontal line that's drawn, it separates the premise statements from the conclusion. So these two sentences, these are the premise statements, and then that last sentence after the horizontal line, that's the conclusion, okay? So let's just, we're going to ignore the conclusion for a moment. So I'm just going to do this because I want us to not even look at that right now. We're going to draw a picture based on just the premise statement. So I have all buildings have windows. So there's the all buildings have windows. So the building set is completely inside the things with windows set. That's the first premise statement. The second premise statement, the structure has no windows, this structure. So when you're pointing out an individual item, you're going to put an X. Now, no windows, that would mean it would have to be outside of the things with windows circle. So I've looked at the two premise statements and I have my diagram. Now I switch gears and I just take a look at, so that's the first two steps. The third step is I just focus in on the conclusion and I need to see, is there a contradiction between the conclusion and the picture, or is everything okay? And when I look at it, this structure is not a building. I see that my X is outside of the building circle. So this argument is valid. The conclusion that the structure is not a building, it doesn't contradict the diagram at all. It goes right along with the diagram. The structure is not a building, the X is outside of the building circle. So that would be considered a valid argument. There's no contradiction there. Okay, let's try another one. Sort of like the last one, but slightly different. All buildings have windows. Now, when we get into looking, we're just focusing on this. I'm going to temporarily ignore the conclusion altogether. When we draw the diagram, we're just looking at the premise statements, and that's it. So all buildings have windows. There's my buildings inside the windows circle. This structure has windows. So now I need to put an X for this structure. This structure has windows, could go here, but it could also go here. I don't know. So when I put in the instructions that you have to list all of the possibilities, this is what I mean. You want to make sure you include all the possible situations. The structure could be in one of those two X's. Those are my options, okay? So now I'm done drawing the picture. I can now look at the conclusion and match it with the picture and see if there's any contradiction. So it says this structure is a building, is my conclusion. There's a problem here because if it's this X, I'm correct. But what if it's this X? So since there's a possibility that it's a contradiction with part of the diagram, okay, this part of the diagram is where it's contradicting. So because of that, because there is a possibility where there's a contradiction there, that one is invalid. The structure could be a building, but not necessarily a building, okay? And since the conclusion contradicts just one of the possibilities, it's invalid. So all it takes for it to be invalid is that there is one possibility that contradicts that conclusion. All it needs is one, and you say invalid. In order for the conclusion to be valid, the picture has to not contradict anything in the conclusion. They have to match up perfectly. I just want to note again that the structure might be a building. The conclusion here, the structure is a building. It might be a building. I'm not saying the structure is not a building. I'm just saying that the argument that's presented has holes in it. So yes, the structure could be a building, but the conclusion is not supported by the statements that come before it. So that's the problem here, okay? So here's another example. No dogs have feathers. This animal has feathers. Now, it's very tempting to keep reading beyond that horizontal line and read the conclusion along with the premise statements. And I would just caution against that and say, cover that up. Draw your pictures. Don't even look at it till you're done drawing your pictures. Otherwise, it's very easy to take the conclusion and start to draw that in the picture, which, of course, if you draw the conclusion in your picture, then you'd be like, oh, yes, it works out great. And then everything would be valid. So you don't want to do that. We want to look just at the premise statements and draw the picture. So no dogs have feathers. So there's the no A or B picture where the two circles do not intersect. No dogs circle does not intersect the animals with feathers circle. So that's the first premise statement. I look at the second one that says this animal has feathers. So this animal has feathers, that means I'm looking at one particular animal, and it's right here in the animals with feathers circle. So this is the picture. Now I'm going to uncover the conclusion and see if there's any contradiction, okay? The conclusion says this animal is not a dog, and the X representing this animal is not in the dog circle. So this argument would be valid. The animal with feathers cannot be anywhere but in that circle, so it's not a dog. And I'm going to take a look and see if there are questions in the question-answer box. Yes, there was a question about will it be recorded. Yes, this is being recorded, and whenever the session is over, I will send out the recording to all of the MAT 115 instructors so they can pass that along. And it will probably not be tonight, though, because it takes a couple hours to convert the file formats before I can upload it into YouTube. So it'll probably be sometime tomorrow that the recording will be made available. Yes, this is being recorded. And the recording will end up after I'm done with the WebEx, converting it to MP4 and then uploading to YouTube. So eventually it'll be on YouTube along with my other webinars. Okay, so let's take a look at this example. All math tests are long. Long tests are difficult. Difficult tests are challenging. All challenging things make me a better person. So just like before, I'm just going to ignore the conclusion while we are drawing the Euler diagram. We don't even want to pay attention to that, okay, because that is not going to be drawn in the diagram. Only the premise statements are drawn in the diagram. And if you notice here, I have a bunch of circles to go along with the premise statement. So all math tests are long. That would mean here's my math test circle, and all math tests are long. I'll let L represent long. So the math test circle is inside the long circle. That's the first sentence. And then the second sentence, long tests are difficult. So that long circle is going to be inside the difficult circle. So That circle is the difficult circle. So far I have all math tests are long tests are difficult. I know I said we'd only have 2 premise statements, but this is an exception to the rule. We have 4 in this one. So the third premise statement, difficult tests are challenging. So the next circle out would be challenging. Okay? So difficult tests are challenging, and then all challenging things make me a better person. So this is things that make me a better person. Make me a better person. Okay. So that's what we have. Math tests are in the middle, then we have long tests, then we have difficult tests, then we have challenging things, and then make me a better person. So now that this diagram is drawn and all filled in, I'm going to reveal my conclusion and see if it's valid. Remember, we're looking to see if there's a contradiction between the picture and the conclusion. The conclusion says all math tests make me a better person. So if that's true, that means the math test circle should be completely inside the make me a better person circle. And if we look at our picture, that's exactly what is shown here. The math test circle is completely inside the better person circle. And so this one is valid. Notice how a valid conclusion may not necessarily be true. I would hope that all math tests make you a better person, but you might disagree with that and think, no, that is not true. But it is a valid argument because this conclusion is based on and supported by these 4 sentences. So even though the conclusion may or may not be true, it really doesn't matter. What matters is that this conclusion does follow logically from the statements above it. Okay? So we're looking at this whole thing as a logical flow of does the conclusion is it logically supported by the premise statement. So in this case, the argument's valid, and again, valid may or may not be true. The conclusion may or may not be true, but that is not what we are testing here. We're testing for the structure of the argument. Okay, so I'm going to check to see if we have anyone have any questions. I don't see any questions. Yes, feel free to type your questions in the chat box or the Q&A box, and so I can address them as we go along. Okay, so here's what I'd like us to do. Since we do have people logged in at this point and it's a live thing, I'm going to give you a moment to type in the chat box whether you think this one is valid or invalid. I've gotten the diagram started. Many adults drive minivans. I am an adult. I drive a minivan. Many. Oh, I'll give you a hint for that one. For many, that would be the same thing as saying some adults drive minivans. Some adults, many adults, it's not all. Many is not all. Many is some. So I would say some adults drive minivans. I am an adult. I drive a minivan. I have some people saying it's invalid. Let's see. Many adults drive minivans. So that would be like some adults drive minivans. So it would look like that. Some adults drive minivans. The word many could be replaced by some. That means at least one adult drives a minivan. So I'm going to put an X right there. Now, I am an adult, which means I am somewhere in the adult circle. So this could be me right here, or this could be me right here. Me. okay? There are two places really that I could be. I'm an adult, so I'm somewhere in the adult circle. So after I have my diagram drawn, I look at the conclusion, I drive a minivan. Well, if this is me, yes, I drive a minivan, but I could also be over here where I'm not in the minivan circle. So those of you that typed invalid, you are correct. That was an invalid argument because I do not necessarily need to be in the those who drive minivans sets. I need to be inside the adult circle, but there are two options here, one in the minivan set circle, one out. And since there's that possibility where I may not be in that set, it's invalid. Okay, let's try another one. All expensive things are desirable. All things that make you live longer are desirable. All things that are expensive make you live longer. Let's see here with this one. All expensive things are desirable. So I'm going to draw all expensive things. So I'll use E for expensive. All expensive things are desirable. So I'll put D for desirable. All expensive things are desirable. It needs to look like that. So I'm going to, in going with our routine here, I'm just going to cross that out because remember when we're drawing the diagram, completely ignore the conclusion. We're just drawing the diagram based on the premise statements. So all things that make you live longer are desirable. So we need to have another circle about living longer. And it could look, it has to be inside the desirable circle. So it could look, I'm going to draw that in a different color. It could look like this. I'll put L for live longer. Could look like that. But it could also look like that because as long as it's inside the desirable circle, it really could be anywhere floating in here. It could be right here as well. It's another place. So this is where I'm saying you need to draw all the possibilities when you are drawing your Euler diagram, put all the possibilities in there because before you look at the conclusion, okay, all the possible ways we could draw that all things that make you live longer are desirable. And those are all the different ways either that we could draw that circle, the live longer circle. Okay, so these are all the possibilities. Now I'm going to read the conclusion and see if anything is contradicted or not. Let's see. All things that are expensive make you live longer. Oh, there's another possibility, by the way. What about this one? I didn't even draw that. Could be like that. Yeah, it's real important that you get all of the possibilities. See, we do have that. All things that are expensive make you live longer. But there is contradiction with with some of the possibilities here, like this one. There's a contradiction with that circle. There's a contradiction with this circle. So because remember, it only takes one contradiction. There's only one case that is needed to say it is an invalid argument. So for this one, this argument is invalid. The conclusion contradicts one of the diagrams that could be drawn from the premise statements. And it could be any of those. It doesn't have, you know, all you need is one. We have more than one contradiction here. This one as well. You know, all things that are expensive make you live longer is one of the ones I didn't draw initially, but that is another way you can draw it. So when you're drawing all the possibilities, try to think of all the different ways that, like, those two circles, the L and the E, could interact, as long as they're both inside the desirable circle. Okay, so that particular example, that was invalid. And I'm just checking for questions, okay? All right, here's another example. Some computers have webcams. My electronic device has a webcam. And conclusion, my electronic device is a computer. So I'm just going to ignore the conclusion while I draw in the picture. The diagram, I got it started right here. Okay, so some computers have webcams. That means there's at least one computer that has a webcam. So I'm going to put an X right here to represent that one computer that has a webcam. And then my electronic device has a webcam. So there's the my again. There's me. Me is right here, and me could be right here because it says I have a webcam. So it could be one of those two places. Let's check to see if there's a contradiction or not. My electronic device is a computer. Well, if I was here, that would be fine. But what if I'm there? I'm not in the computer circle. So for this one, it's invalid. My electronic device could be in the webcam set, but doesn't have to be, sorry, it could be in the, it has to be in the webcam set. Could be in the computers or could not be in the computers. But that is definitely an invalid conclusion because of the contradiction that it has to be a computer. If I'm here, then it's not a computer. Okay. Now, this one. Let me scroll down so you guys can see. Some cars have airbags. Some cars have heated seats. Some cars with airbags have heated seats. Now, let's ignore the conclusion while we draw the pictures, okay? This is one way to draw. Now we have cars, airbags, and heated seats. Some cars have airbags, means that between the car circle and the airbag circle, there is at least one. Some cars have heated seats, so between the car circle and the heated seat circle, there is at least one. Now, it could be that instead of these two X's there, it could be that they're actually in the same. Like if I do this, that still works. Some cars have airbags, some cars have heated seats. Putting that X in that one spot works for both of those premise statements. What if it looks like this? I'm going to cross this out again. And we say some cars have airbags, some cars have heated seats. Could look like that. So I'm just trying to draw the possibilities, all the possible ways that we could draw these premise statements. This is one possible way where the airbags and the heated seat circles do not overlap, and we have one X representing at least one car with an airbag, a different X representing at least one car with a heated seat. So this is one possibility, and this is the other possibility where the X, the one X that's in the cars, the airbags, and the heated seat circles all takes care of the premise statement. Some cars have airbags, some cars have heated seats. That also works. It's another possible way to draw the diagram. Now let's see if there's any contradiction with the conclusion. Some cars with airbags have heated seats. No contradiction there. But what about this one? Some cars with airbags have heated seats. Same problem. Notice that there is a contradiction with this particular picture of the situation where I don't have cars with airbags with heated seats. So because of this particular diagram, remember it just takes one that would contradict it, that would be invalid. Okay? I know this right here makes it invalid. This is fine. We don't have a contradiction with this one, but the premise statements could also be drawn this way. And if they're drawn this way, there's a contradiction with the conclusion. Okay. So again, it's real important that you draw all the different possible situations. What determines if the circles intersect? That's a good question. How do I know the circles intersect? I don't, actually. I don't know if they intersect, and I don't know that they don't intersect. I assume you're asking about the airbags and the heated seats, because I do know the airbags and the car circles intersect because some cars have airbags, and the cars and the heated seat circle intersect because some cars have heated seats. But I don't know if the airbags and the heated seat circles intersect or if they don't intersect, which is why I'm drawing it this way where they do intersect, and I'm drawing it this way where they don't intersect, because I'm not told in the premise statements. Remember, we're ignoring this. When we draw the pictures, I ignore the conclusion. So if I just look at those two sentences, some cars have airbags, some cars have heated seats, I don't know if they intersect or not. So I'm drawing both pictures. I'm drawing this picture and I'm drawing this picture because I need to look at all the possible ways I could draw the picture. So I really don't know if they intersect. I'm not told one way or another. Like, again, I'm ignoring the conclusion because you draw the picture just from the premise statement. So when I look at that, I can't tell if the airbags and the heated seats intersect. Okay, and then someone asked, how do you know which diagram to use? Which diagram to use? You go back to the sum A. Both of these sentences start out sum. And if we go back to some of where we started at the beginning here, let me pull that up. The sum A RB looks like this. Sum A RB looks like that, where you have the circles intersecting with an X in the intersection. Anytime you see sum A RB like that format, sometimes instead of the word sum, it'll say many. Sometimes it'll say many ARB, but as long as it doesn't say all, because all ARB is a different diagram. But sum ARB looks like that, where they intersect and you put an X in the middle. This is no ARB, is where they don't intersect at all. So I do know that the car circle, in this example, I know the car circle and the airbag circle do intersect because it says some cars have airbags. So I know I'm going back to this particular picture, this particular picture that it's in general, anytime it's some ARB, this is how you draw it. Let me go back to where we were right there. Okay. Here's a really good question. One drawing makes it valid, and the other drawing does not, so how do you know which one to pick? Because if I look at this drawing, it's valid. If I look at this drawing, it's invalid. And so how do I know which diagram to look at to determine valid or invalid? That's a really good question. If there is any diagram that makes it invalid, then you automatically put invalid. The only time you write valid is if every single possible picture shows valid. So because this picture shows invalid, I have to pick that my answer is invalid. Okay? The only time you write valid is if every single possibility shows valid. You only need one possibility to show invalid. So that's a really good question. So yes, that one's invalid. Okay, so here's another example. I have the picture started. Take a look at that. Some teachers are organized. Mrs. R is a teacher. And then the conclusion would be Mrs. R is organized. And in the chat box there, put what you would think that is. Is that valid or invalid? Oh, and there's also a question about how do you know the amount of circles needed. So I'll address that as well. Okay, so some people are saying this is valid. Let's see. Some teachers are organized. So some A or B, that's this, where you draw the X in the middle of the two intersecting pieces. And then, okay, so I'm ignoring this, right? Some teachers are organized. I put an X right there. Mrs. R is a teacher. So Mrs. R has to be inside the teacher circle. So Mrs. R could be right there, or Mrs. R could be right there. Those are two places where Mrs. R could be, because Mrs. R just has to be inside the teacher circle somewhere. So then, now my picture's drawn, I'm going to look at the conclusion. Mrs. R is organized. Well, if Mrs. R is in this spot, then yes, Mrs. R is organized. But what if Mrs. R is not in that spot? What if, let's see, no, there's one right there. What if Mrs. R is over here? Mrs. R doesn't have to be in the intersection of teacher and organized people. Mrs. R could be over here. So in that case, that's an invalid. And remember, it only takes one way that you draw this picture for it to be invalid, for it to be considered invalid. And this is the one way. If I drew it like, oops, if I drew it like this and I put Mrs. R in the intersection, it's valid. But I could, Mrs. R is a teacher, which means Mrs. R has to be in the teacher circle somewhere. Doesn't have to be in the intersection. I could put Mrs. R right here, and in that case, it's invalid. And it only takes one picture to show invalid, and because of this one picture, this argument is invalid because of that one picture. Now, someone asked, how do I know how many circles to draw? Well, basically, think of the nouns, like in this particular one. Teachers, organized people. Like some teachers are organized. That'd be like the sum A, R, B. We need a circle for A, we need a circle for B. Now, this Mrs. R, anytime it's like an individual item, you don't need a circle for an individual item. You just need an X, okay? Or an R in this case. We used an R. But the sum A, R, B, going back to what that looks like, here's A, here's B, and we put an X right there. That's what sum A, R, B looks like, okay? And I did not use a circle for Mrs. R because it's just one item. Just like whenever we were looking back at, let's see, let me go back. This one. I have computers, that's a noun there, and devices, webcams, that's one right there. And again, this is like sum A, R, B again. But my electronic device, I don't need a circle for my electronic device because it's not a group of things. The circles represent groups of things. But my electronic device is just one item, so I don't use a circle for just one item. I just put like an X to represent one item. Okay. Let's see. All right, so that one's invalid. And there'll be some questions that it's worded kind of different. Let me check the question box again. Are all the sentences that has some in it, oh, are they always invalid? No. Just because there's the word some doesn't mean it's invalid all the time. I know a lot of the ones we've done are invalid, but you can't just say just because, I'm sorry, I'm answering a question. Just because there's the word some, don't automatically think it's invalid. That's a good question, too. I know it seems like that, but not always. You can't just make that conclusion. Okay, so here we're going to have actually 3 premise statements, and then we'll look at each conclusion. These are all premise statements right here. So we can draw the diagram based on that. And then from there, look at conclusions to see which ones are valid or invalid. So this way we're just dealing with one picture and not have to keep redrawing pictures, okay? So all people who drive contribute to air pollution. all people who contribute to air pollution make life a little worse. Some people who live in a suburb make life a little worse. So we need to draw a picture for that. All people who drive contribute to air pollution. So here's the drive and the air pollution. All people who drive contribute to air pollution, and that's the all ARB circle, right? All people who contribute to air pollution make life a little worse. So this is worse. All people who contribute to air pollution make life a little worse. So it looks like that. Last sentence, last premise statement. Some people who live in a suburb make life a little worse. So that's the sum ARB. Some people who live in a suburb make life a little worse. So what are the ways we could draw that? Well, I'm going to put S for suburb. Could look like that, where there's an X right here, right? Some people who live in a suburb make life a little worse. Could also be where it kind of goes like this, but could also be where it even goes into the drive circle. Could do that. Or it could look like this. Some people who drive, what's the statement again? Some people who live in a suburb make life a little worse. Some people who live in a suburb make life a little worse. So we just need to have it where it's kind of overlapping the make life a little worse. So it could be like that, or we could have it like this. So I'm just trying to draw all the possible ways. See, I haven't even read the conclusion yet. I'm just trying to draw all the possible ways where some people who live in some people who live in the suburb make life a little worse. So looks kind of like that. Got all these possible suburb circles, okay? And we don't put the suburb circle completely inside the worst circle. Well, can we? No. Some people who, that doesn't work. That doesn't work. There. Those are all the possibilities, because we cannot put the suburb circle completely inside the worst circle. It has to be out of the worst circle a little bit, and this is the entire worst circle. So we're trying to get it where there's some inside the worst circle, some outside the worst circle, because it's some, because it's worded some. Some people who live in a suburb make life a little worse. Okay, now let's look at this conclusion. Some people, we're going to see if it's valid or invalid. Some people who live in a suburb contribute to air pollution. Type in the text box what you think that conclusion would be true, valid or invalid. These are not true-false questions. Let's see. Some people are saying valid. Some people are not answering. Okay, so let's see. Some people who live in a suburb contribute to air pollution. Well, where's the air pollution circle? That's right here. So in order for that to be valid, this suburb circle has to be intersecting the air pollution circle. But what about this case? It's not intersecting the air pollution circle at all. And remember, it only takes one to say invalid. So this one would be invalid. Because of this, some people who live in a suburb contribute to air pollution would mean that this has to be overlapped, the air pollution, but it's not. Okay. So same picture. This is the drive air pollution worse. And our suburb circles look like that, or like that, or like that. Okay, so these are my suburb circles. Some people who live in a suburb drive. Some people who live in a suburb drive for that conclusion. Well, what do you think about that one? Some people who live in a suburb drive. What do you think? Now nobody wants to answer. Invalid. I'm looking at a lot of invalids. I'm so very happy. Because what about this? This is an example of, you know, where you can live in a suburb and not drive. So that would definitely be invalid. Okay, so we have our drive, air pollution, make life worse, live in a suburb could be that, or live in a suburb could be that. All right, so suburban residents never drive. Suburban residents never drive. That means that the suburb circle never intersects the drive circle. But what about this right here? So all it takes is one example, just one picture, and we have invalid for that one. Takes just one picture, yep. All right, let's see here. Drive, air pollution, makes life worse. Suburb, suburb, suburb. I know it's a pain to have to redraw, but it's the way it worked out. Some people who contribute to air pollution live in a suburb. Some people who contribute to air pollution live in a suburb. Well, what about this one? These suburb people don't contribute to air pollution. It looks like we have another invalid, but don't think just because of the word some, it's always going to be invalid. You can't make that conclusion. Okay, I think you guys are getting the hang of it. Here's drive, air pollution, makes life worse. Suburb, suburb, suburb. Contributes. Okay, some people who live a little, who make life a little worse, live in a suburb. Some people who make life a little worse live in a suburb. What do you think for that one? Some people who make life a little worse live in a suburb. That means that the suburb circle is intersecting the worst circle for all the possibilities. And that's what we have here. This is intersecting the worst, this is intersecting the worst, this is intersecting the worst circle. So we actually found one with a sum that's valid. And I know we're running out of time, so we're almost done here though. So drive, air pollution, makes life worse, lives in the suburb, lives in a suburb, lives in a suburb. Okay. All people who drive make life a little worse. All people who drive make life a little worse. What do you think for that one? I see a lot of valid being typed. That is correct. That would be valid because the entire drive circle is inside make life a little worse circle, so that would be valid. Okay. So I just wanted to, summarize what we've done here, that we talked about the difference between Venn and Euler, and then looked at Euler diagrams, hopefully with enough examples for you to help understand. And I'm checking to see if there's any questions in the chat boxes. I don't see any questions. I just want to remind you about my email, and also that this is not intended to cover absolutely everything on Euler diagrams. Still, watch the videos, read the book, that kind of thing. I will be sending out the recording and also the notes that I used for tonight after I hopefully fix some of the typos. But I will be sending that out as well. So I just wanted to say thank you again for coming to this webinar, and I'm going to go ahead and stop the recording and get this stopped and go ahead and shut it down. But if you have any other questions, I don't see any in the chat boxes. So you're very welcome. For someone said thank you for doing the webinar, and feel free to email me with any additional questions. Okay, God bless.